So hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the chat window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions from the chat window. Your questions in the chat window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Fletcher Malcom from Repligen.
Thank you, Leah. This is Fletcher Malcom with Repligen, and today's talk is going to focus on scalable pre-packed column performance from 1 mil to 100 liters. And I focus on our chromatography products at Repligen, have a long history with our Opus columns. And in today's talk, we're going to focus on a new topic, hasn't been presented before, which is scale-up challenges in chromatography and how pre-packed columns can help solve some of those challenges. So this is new data, and we're excited to bring it to you today. To start, we'll just have a quick corporate introduction with Repligen. We're one of the fastest growing companies in North America, a public company that is. And we have about 500 employees headquartered outside of Boston. We focus on hollow fiber and flat sheet filtration technologies, pre-packed columns, and protein A ligand manufacturing, which is our legacy product at Repligen. The breakdown of revenue is shown on the left-hand pie chart, and that is for updated for 2018. So gives you a little bit of idea about Repligen, and now focusing on pre-packed columns, looking at the journey from small scale or early phase development all the way to GMP production. There are many steps in this process. Maybe starts with high throughput screening, large numbers of parameters, whether it be chromatography methods, solutions, etc., or even resins that are screened. And then as we narrow the parameters down, columns get a little bit larger, the process gets scaled up to typical bench scale type of experiments, and then from there to a pilot scale, and that's where we're looking for a defined process. And then finally to GMP production, process could be validated or maybe just qualified depending on the phase of development. And so through all these steps, pre-packed columns are available to help aid in scaling. And today what we're going to look at is some of the data from bench scale to large scale chromatography columns and how the chromatography scales. And when you're starting down this journey of scalability, when we talk to customers, we hear many different questions, but three of them are summarized here on the slide, and that is how important are differences in column packing methods? If we use packing method A versus packing method B, do we get different chromatography results? And then column hardware considerations. If you have a different column hardware from small to large, which is common, either in pre-packed formats or in self-packed formats, do you have to worry about how that chromatography scales? And then from a process side, how easily can your process be scaled from bench to production? And so for pre-packed columns, we can help eliminate these top two questions. At Repligen, we focus on having consistent column packing methods, and we've developed our hardware to be optimal for chromatography. And so, as we'll show with the data that follows in this presentation, these two considerations no longer are things that you have to worry about. And that means you can focus on this central question here, that is your process scalability. And you don't have to worry about these column issues. And so as we start down this journey from the small bench scale development with, for example, RoboColumns or mini-chrome columns, we can demonstrate that even the smallest formats, that is the RoboColumn formats in, say, a TCAN system, can produce very similar results. And that's what's shown in these two chromatograms down at the bottom of the slide, where in pink diamonds we have the RoboColumn chromatogram or data points, and in the blue, we have the mini-chrome. And so you can see that even a RoboColumn produces similar results to an actual column. And so what this shows, and what others have already presented on, is the RoboColumn technology can be used for process characterization, meaning that you can use even the smallest of chromatography formats to then produce scalable results. So this data has been previously published, also a number of different papers that are shown on the slide. And so what we wanted to show next was how things scale to larger sizes. And there had been a lot of work done previously with the mini-chrome columns and some of the valley-chrome columns shown here on the slide. But what we've done recently in the past year and a half is look at the larger column sizes, the 10s, the 45s, the 60s. How does chromatography scale from all of the sizes that we offer today? And so to do that, we looked at two different experiments within this case study. It was a collaboration with the Dr. Jungbauer lab in Austria. And these two experiments were the protein binding capacity assay, where we loaded lysosome to 100% breakthrough, so we'll look at some breakthrough curves. And then the chromatographic separation efficiency, whereby we're separating these three different species here, the lysosome, the ribonuclease A, and cytochrome C. This is all done with a model cation exchange resin and different chromatography equipment, which is employed as we scale up to the larger sizes. So the first assay is first experiment is the lysosome breakthrough curve. So we looked at the breakthrough curves of all the columns from very small, 1 mil, to a 45 centimeter column. The only reason why we didn't go to larger 60 centimeter columns was it took over 4 hours just to purify the lysosome to get it on a 45 centimeter column, and we didn't have enough time to purify that amount of material for a 60 centimeter column. But as you can see, all of the breakthrough curves look similar, and they have similar slopes, except for these smaller diameter columns or smaller column volume columns, which differences are due to the extra volume associated with the chromatography system, the volume of the column, in other words, not 100% optimized. Additional differences, the ones that you can see with the different colored bands, are due to the conductivity load solution. So what we found is that the assay was very sensitive to differences of conductivity of that load solution, and that those differences produced some of the variation that we see. But as we look at the right side of the slide, what we can see is that the common measure, one of the common measures of performance, dynamic binding capacity, is consistent between the smallest of formats, the 1 mil column, all the way up to the 45 or 32 liter column. So that's the binding capacity or summary of the binding capacity data. And now if we look at the gradient separation, what we're doing here is a simple salt gradient, 3 steps, as seen on the slide, 1, 2, 3, and those are designed to elute lysosome, ribonuclease A, and cytochrome C. And so what we have on the slide here are the chromatograms from the 0.8 to by 20 centimeter column, which is a 10 milliliter column, all the way up to a 60 by 20 centimeter column, which is a 57 liter column. And so what you see is that the chromatography is consistent. The peaks overlay not perfectly, but very close. Some of the differences are due to the different systems, chromatography systems used. But again, you see that the chromatography is consistent, is scalable from a 10 mil size all the way up to a 57 liter column size. And this data can further be summarized by the protein purity data. And here we're showing the load plus the 3 different gradient steps. So step 1, where we're eluting the ribonuclease A, step 2, the cytochrome C, and step 3, the lysosome. And you can see that throughout all the column sizes from the 1 mil all the way to the 57 liter column, the results are similar. And so we don't see any significant differences in the purity data which demonstrate that the packed bed performance is maintained even though you may have slightly different packing methods, even though you might have slightly different hardware as the columns scale. And so at the time when we did this work, we didn't have our 80 centimeter column yet. It was in development. And so we'd like to go back and do some of the work with the 80 as well, but we haven't done that yet. So today what we can show is when we look at just column packing data, plate count and asymmetry for two model resins, in particular, we can focus on the resin that was used in the study. So the same cation exchange resin used for the protein efficiency separation, the gradient separation, as well as the binding capacity data we have here on the right side of the slide, and we can see consistent chromatography results from the 10 to the 80 as it pertains to plate count and asymmetry. So in summary, the data shows that we have consistent binding capacity across the column sizes as shown. So we can check that box. The separation efficiency, so when you're performing a gradient, does the chromatography scale from small to large? We've demonstrated that it does. We demonstrate that there is packed bed uniformity across the different sizes. And then finally, as we consider the largest pre-packed columns, the 80 centimeter pre-packed columns, we see the packed bed performance is consistent with the smaller diameter columns, meaning that you can go from very small bench scale experiments using RoboColumns, for example, all the way up to an 80 centimeter column and conserve that packed bed performance. And that enables the chromatographic scalability from large to small. So with that, just wanted to thank many individuals who were involved in this work, both from Dr. Jungbauer's lab as well as at Repligen. Those individuals are listed on the slide. And so with that, I will take any questions.
Okay, great. Thank you, Fletcher. So the first question is, why might you see differences in small bench scale columns and larger columns for production, both for self-packed and pre-packed?
Right, so why might you see differences between a small column and a large column? It's a question that we get quite frequently. A lot of the time, what we find is that some of the differences may be due to the chromatography systems used, the volumes associated with those systems. And so oftentimes there's a system aspect to differences in using small columns to large columns. And then from a chromatography column perspective, there are differences in terms of how the wall effects of the column help to support the packed bed. And that can influence characteristics like pressure flow. We sometimes see differences in plate count asymmetry as well, but that's resin dependent. Pressure versus flow, sometimes also we see differences when going from a small column, say a 10 centimeter column, to a larger column where the 10 centimeter column, the walls of the column help support the bed in a greater manner. So usually when we see differences from large to small, oftentimes it's either the column hardware, slight differences in the wall effects of the small column to large column, or the system differences.
Okay. How are the scale-up parameters maintained between the different column sizes?
Is that a specific question? Sorry, I'm looking for a little bit more clarity on that question. So scale-up parameters, what type of parameters would you be looking for? Are you looking for parameters in column packing, or parameters in the actual column design, or parameters in some of the experiments that we showed?
Okay, well, hopefully we'll add more to the question. We'll go on to the next question.
Here,
details
you just
here.
replied. Okay. So such as bed heights, linear velocity, etc. Okay, so depending on the type of assay that or type of step that you're running, you may want to maintain bed heights. Typically, we do see bed heights that are maintained once you get beyond sort of the RoboColumn scale, or you can maintain the things like linear velocity. That's typically maintained as you scale from small to large. Also, some of the binding characteristics of the resin is important from scaling. So yes, we do typically see bed heights maintained, linear velocity maintained, but some of those parameters can be influenced also by chromatography system, production volumes, flow rates, pressure limits, etc. So occasionally we see things like linear velocity actually decrease as you scale. And so it's really dependent on the process. But from a column perspective, if we just think about the column, yes, usually we would keep the bed height consistent once we get to sort of above the RoboColumn, the initial screening size.
How or is it possible for pre-packed columns to be integrated into continuous chromatography system?
Yeah, that's a really interesting question. So today the solutions are, of course, you have a standalone continuous processing system and then pre-packed columns. And we haven't, me personally, I haven't seen any sort of fully integrated system, but I'm sure there's probably some things out in development that I'm not aware of. But today I think, it is very much two different devices, the system and the column. In the future, could they be more combined, perhaps, or more integrated, perhaps? But you still always have you still always have to be able to change out the columns. So you still have a piece of the equipment, even if it was in a chromatography column format, that would have to be pulled out and then installed again. So perhaps better integration is something that we can work on as an industry in terms of that system and the column, or more seamless integration, I think is a future, something we can work on. But full integration, that could be slightly challenging, depending on how you think about it.
Okay, great. Thanks, Fletcher.
Thank you.
And thanks for joining us. The recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. Look forward to future BioProcess International Ask the Expert webcast. Look for those announcements in your inbox. Bye.